Welcome again to our last chapter in our Unit 4. We're going to talk about sound beams today. So we're going to learn a little bit more about the anatomy of our sound beam, kind of like we learned about the anatomy of our transducer. We're going to look at how the sound is created from a very simple transducer. So just like we did with transducers, we learned about a very basic transducer. You're going to learn about a very basic sound beam that is created by that basic transducer. So the sound beams that we'll be talking about today are sound beams created by a single disc shaped element, and we're going to look at it as if it was creating a continuous wave. Again, we're going to take this knowledge of how sound beams are created and what they look like in space, and it loosely, well, more than loosely, it is what's happening with our transducers, but it's again just scratching the surface of the complexities of the physics that are happening in our diagnostic imaging transducers, our modern ones. So just keep that in mind, but again, learning these basics are going to give us that basic understanding of how the sound beams operate. When a sound beam leaves a transducer, the wideness or the width of the transducer is going to be the same as the transducer face. It can't be any bigger than the transducer. And what it's going to do then is taper a little bit towards the center. And once it tapers, it's going to again become wide and diverge into kind of oblivion. It just keeps diverging until it's relatively non-existent as far as sound beams go. So we need to know what these areas of the sound beam are called. Again, the anatomy of the sound beam. So there's 5 areas that we need to know. The first is the focus, which is right at the very center, the very thinnest part of our beam. We also need to know the near zone, which is the area near the transducer. The far zone, which I'm sure you can guess is the area far from the transducer. We have the focal length then, which is the distance from the transducer face to the focus. And then we have the focal zone, which is kind of an even area into the far and near zone, sitting either side of the focal point. Now what you'll see as we go through these, there are multiple names for some of these areas. Make sure that you know all of them. They're all free game for test questions. So let's look at each of these a little bit more in detail. So the focus, which is also known as the focal point, is going to be located where the beam is narrowest. And we'll learn why we can change the focus in a later chapter. But when you change your focus on your machine, you are changing where the focal point is. So you are changing the shape of the sound beam. So again, the focus is the most narrow point of the sound beam. When we're discussing single disc elements, as we are for this chapter, the focus is going to be where the beam is about half the size of the beam as it left the transducer. So again, half the size of the face of the transducer is typically where our focus is. That's as thin as it's going to get. Our near zone then again sits near the transducer. It's the area from the transducer face to the focal point. The near field has a couple different names. It's known as near zone, near field, or the Fresnel zone. So boards love to use these other names as Fresnel. Love it. So make sure you know Fresnel goes with near. And again, it's located from the transducer to the focal point. The focal length then is a depth measurement. It is going to be from the transducer face to the focus, and it actually is also the length of the near zone. The far zone then is the area beyond the focus where the beam begins to diverge, and this is going to be also known as the far field or the Fraunhofer zone. So I remember Fraunhofer goes with far, because we have F-R-A, F-A-R. So we kind of have similar letters in the beginning of it. And it's just kind of fun. You get to say Fraunhofer zone. Sounds very German to me. Anyway, far zone, again, is going to be located on the far side of the focal point where the beam is starting to diverge. And then the focal zone is an area that surrounds the focus. So we saw from our original picture, we had the focus in the center, and then there was kind of this equal area on either side of it. So half of the focal zone does sit in the near field, and then half of it sits in the far field. When we are imaging, we want the anatomy that we are most interested in to sit within this focal zone. That is because the beam is the narrowest at this point and offers better detail and resolution through this area. I mentioned on the focal point slide that the focal point is found when the diameter of the beam is half of what it was at the transducer. So remember, the beam transducer starts as the same width as the transducer face. It'll narrow down to its thinnest where it's half of that. It'll widen again to a point where it gets to be the transducer face width again, and then beyond that point it's just greater than the transducer face. So let's just look at an example here. If we have our transducer here, beam is coming out and then it diverges. Let's say that our transducer face is 10 millimeters. That means that our focus has a width of 5 millimeters because it's half of this. And then again, the beam will diverge again to that 10 millimeters. Once we get past this point where it is equal to the transducer face, anything back here is going to be greater than 10 millimeters. So you might say that it's greater than D, or we can estimate if you're given a question, say we have point A, B, C, and D. Point A would be 10 millimeters, point B would be 5, point C would be 10, and then if we said point D, if there was an option for 12, you could guess that. If it just said greater than 10, that would also be appropriate. So it's just kind of the concept that we are now wider than what the beam originally started as. So just kind of as a summary of everything that we talked about, again, it's going to be mostly memorization of what these areas are called and where they are located. We know that the beam starts at the probe or at the transducer face. It goes through the near field, through the focus, and then into the far field. If we go from transducer face to the focus, that is our focal length. And then the focus is the center of the focal zone. Let's just draw it again just to help see it in another way. Here's our transducer face. Here's our beam profile. Our focus is where the beam is narrowest. That's our focus. Our focal zone then, remember, sits evenly into the near field and the far field. And this is where we want our anatomy. This is our happy place for our anatomy. The focal length, if I could get out a ruler and measure from the probe down to the focus, if I could measure that distance, that would be our focal length. That's a distance. The near field then is from focus back to the transducer. Happens to also be in line with the focal length. And then the far field is anything beyond the focal point. The focus, you might see, is also the end of the focal length. It's the end of the near zone, or you can say it's the beginning of the far zone. So again, a few different idea concepts of the focal point. When we are imaging, we always teach you to put your focus at or below the area of interest. And again, that's because of this focal zone here. Anything that's in that focal zone is going to be provided better detail because that is where our beam is thinnest. So let's first look at how we determine the focal depth. And This isn't going to so much be, here's a formula, plug the numbers in and figure it out. This is going to be more based on some concepts that you need to know and how they are related to one another. And those concepts are mostly going to be, what is the transducer diameter? So what is the transducer's width? And the second one is, what is the frequency of the sound that is coming out? Now when we talk about our current transducers have adjustable frequencies, we have adjustable foci, and that's because of the way that they're made, and they use phased electrical volts. And we'll talk about that more. But today we are going to look at how those single disc transducers with the one PZT element, those are fixed focuses, and how those are affected by the diameter and the sound. So let's first look at focal depth and transducer diameter. When we increase the diameter of the transducer, the focal depth becomes deeper. When we decrease the diameter of the transducer, the focal depth becomes shallow. So transducer diameter and focal depth are going to be directly related. The wider the diameter, the deeper the focal depth. So here I have two transducer faces. The green one is narrow, the purple one is wide. Our green one will have a shallow focus compared to our purple one, which will have a deep focus. Okay. So wider diameter equals wider focal depth. Thinner diameter equals thinner or shallower focal depth. So that's the first concept of focal depth, has to do with the width of the transducer. So again, here's another image. Small diameter equals shallow focus, where large diameters have deep focuses. Now remember, frequency was the other concept that changed where the focal depth is. So when we increase the frequency, the focal depth is going to become deeper. When we decrease the frequency, the focal depth will be more shallow. Because of that then, transducer frequency and focal depth are also directly related. When you increase the frequency, the focal depth becomes deeper. So we're back to our transducers. They have equal diameters. The one on the left here is a 10 megahertz transducer, where the one on the right is a 5 megahertz transducer. We can see then when we increase our frequency, our depth becomes lower. When we decrease the frequency, the depth decreases or becomes more shallow. So higher frequency equals more depth. Low frequencies equals shallow focal depth. And again, to show a picture of it, when our diameters are equal, but the frequencies change, low frequencies will have shallow, and high frequencies will have deep. So you might be thinking, after discussing all of these relationships between diameter and frequency, that hey, you've been telling us all along that high frequencies are good for shallow imaging, but now you just told me that high frequencies have deep focal depth. How does that work? Well, when manufacturers create high frequency probes, they're going to make the crystals itty bitty. They're going to make them super tiny. And remember, tiny diameters equal shallow focuses. So they counteract the fact that high frequency is going to have a deep focus by making an itty bitty diameter which will then decrease the focus of that beam. So again, just to recap. So just as a recap, shallow focal depths compared to our deep focal depths. Shallow ones are going to be produced by small diameters and low frequencies, where deep focal depths are going to be large diameters and high frequencies. So when this increases and this increases, this will increase. When this decreases and this decreases, this decreases. Okay, so they're all directly related to one another. So let's take a look at some of the math. And this is another formula that you don't need to know. Do not waste your time memorizing it, but I just want to show you how the diameter and the frequency of the transducer change the focal depth. So if we look at probe A, it has a diameter of 2 millimeters and a frequency of 15 megahertz. Probe B then has a diameter of 4 millimeters and the same frequency, 4 megahertz. So we're looking at how the diameter changes where the focal depth is. So the focal depth formula is on the bottom here. Again, we're just showing you how these are related to one another. See how both diameter and frequency are above the division. They're the numerator of this division. That means they are both going to be directly related to the focal depth. Anything that's above the line in division will be directly related to the equal part. So if we plug in our 2 millimeters into the diameter and our 15 megahertz into the frequency, we get a focal depth that is 10 millimeters deep. So small diameter, shallow focal depth. Compare that to a 4 millimeter crystal that will create a probe depth of 40 millimeters. Large diameter, deep focal depth. In example 2 then, we're going to keep the diameters of the crystals the same but change the frequencies. Again, probe A has a high frequency, where probe B has a low frequency. Again, we'll plug those numbers in. We see that probe A with the high frequency has the deep focal depth, where probe B and the low frequency has the shallow focal depth. I also want to point out, again, I'm going to go back one slide. Look at the difference. 2 millimeter difference made a large difference in the focal depth. And that's because diameter is squared in our equation. When we go to example 2, there's actually a pretty large change in frequency here, but a very small difference in depth. So when we say that high frequencies have deep focal depth, but we can fix that by making these the crystal diameters, very small. The other concept that you need to know about how the beam profile appears is how the beam starts to diverge in the far field. So we know that as the beam travels out of the transducer, it's going to start to narrow, and when it gets to that smallest point, that's the focus. After the focus, it's going to start to widen or diverge in the far field. And that divergence and the rate at which it diverges is again determined by the transducer diameter and the frequency of the sound. So when we are looking at transducer diameter versus the sound beam divergence, we know that smaller crystals are going to create beams that diverge more, where larger crystals are going to create beams that diverge less. So crystal diameter and sound beam divergence are inversely related. If the transducer diameter decreases, then the beam is going to become wider quicker. When we use smaller diameter crystals, they are going to have poor resolution in the far field, where large diameter crystals are going to have improved lateral resolution in the far field. So let's take a look at this. Again, we have a small crystal and a large crystal. And we're talking about the divergence that happens in the far field. So the small crystal is going to narrow and then diverge a lot in the far field, where our large crystal is going to do very little divergence. Look at the difference between the two. Large crystals diverge less, where our tiny crystals diverged a lot. So, small diameter equals large divergence. Large diameter equals very little divergence. And again, just another picture to show you what we're seeing. So small diameter, more divergence, large diameter, less divergence. Just like with focal depth, the frequency and the sound beam divergence are also related. When we have higher frequency transducers, the sound beam is going to have less divergence, where when we have low frequency transducers, our sound beam will have more divergence. So frequency and sound beam are inversely related as well. If the frequency decreases, then the beam divergence will increase. So again, back to the whiteboard. This transducer here is 5 megahertz. It's a low frequency transducer, which means that it'll have a lot of divergence, versus the 10 megahertz frequency, which has low divergence. So lower frequencies equals more divergence, high frequency equals less divergence. So we have learned that with divergence, they are inversely related to the frequency and diameter, where focal depth are going to be directly related to frequency and diameter. And again, another image kind of illustrating the changes. And just like with our sound beam and focal depth, we have a formula that kind of illustrates what is happening with beam divergence and frequency. So remember, in our focal depth formula, diameter and frequency were on top of the beam, or of the bar. That meant that they were directly related to focal depth. In our divergence formula, they're underneath. They are the denominator of the formula. So that means that these two items are going to be inversely related to the item that everything is equal to. So if we plug our numbers into it, we see that our higher frequency has a lower angle of divergence compared to the divergence of the low frequency. When you have higher degrees, it means that we have more divergence happening. We can look at our example 2. Again, same idea. We've left the frequencies equal. Now we have changed the diameter of our probes. We can see that our thin probe has a very large divergence, where our wider probe has a very low divergence. They are inversely related to divergence. So I just want to kind of recap everything, write a few things down, just so we can see it again, all in relationship to one another. I think the concepts themselves aren't very hard to understand, but it's the fact that we're kind of throwing them all in to one area and then trying to remember how they affect the beam gets it kind of muddled. So I encourage you again to figure out a way to memorize this. If you have any really good tips or tricks on how to memorize this, make sure to include that in your post this week. I would love to see something awesome like that. But remember that our focal depth is going to be equal to the diameter squared times the frequency divided by 6, where our divergence is going to be equal to 1.85 divided by diameter multiplied by frequency. So I like to write out our formulas just again to reiterate, anything that's on top increases, our equal is going to increase. If it's on the bottom and this increases, then this is going to decrease. So that shows us directly related and inversely related. So if we can get this picture in our mind, remember this concept here. So I like that this will help us to kind of visualize, again, that when that diameter increases, our focal depth is deep. It increases in length. When our frequency increases, again, our focal depth will also increase in length. It'll be deeper. Where beam divergence, when we increase our diameter, our focal depth becomes shallow. And when our frequency increases, again, our focal depth will become shallow. And then, of course, the same is true for the opposite. The only thing that I don't like about writing arrows and talking about it when we're talking about it is I've been trying to say, shallow, deeper, larger, wider. That makes it kind of hard to visualize. So focal depth decreases, but when you think of the arrow, you think of it being kind of down deeper. So just remember, focal depth decreasing means focal depth is shallow. You have to remember that part of it. So if you can make a nice chart to kind of keep track of everything, I think you will be in a good spot for remembering these concepts. Okay, just a couple more things to go over for this, and we are done with chapter 9. We are cruising, you guys. So spherical waves are a concept that when tiny diameter PCT crystals emit their sound, they don't really emit that hourglass shape that we've been looking at this whole time. They actually emit more of a V shape. And so that V-shaped beam is a spherical wave. And it has a couple different names. It goes by Huygens wavelets, diffraction patterns, or spherical waves. So again, when the tiny crystals emit their sound, little crystals, they're going to emit these kind of V-shaped waves instead of larger crystals, which do more of that hourglass. Okay, so that's what we're talking about with spherical waves. Tiny crystals diverge very, very quickly, and so they look more like a V shape. So Huygens' principle then is based on those V shapes and how they interact with one another. So if we think of really large crystals creating that hourglass, what we can actually think of the really large crystal being is a bunch of tiny itty bitty little sound sources that are working together to create that hourglass shape. So there's lots of sound sources within the large crystal. And when those sound sources, those tiny sound sources, create their sound, remember they make those V shapes. So as all those little V shapes come out of the large crystal, we expect some to deconstruct and we expect some to construct with one another. And what we end up getting is some cancellations and amplifications and changes of the wave, and that is where we start to get our hourglass shape. And it's just the way that all those little V's interact with one another. So again, we have our large crystal that has tiny itty bitty sound sources within it. Those tiny itty bitty sound sources create the V's. The V's interact with one another, constructing and deconstructing one another to create our final hourglass shape. So Huygens' principle tells us that those tiny V's work together to make the hourglass. And that, everybody, is the end of sound beam anatomy. So remember how frequency and diameter affect focal depth and divergence. Know what spherical waves are and how they apply to Huygens' principle. And then know all the parts of the sound beam, the different names for all the parts of the sound beam. That's going to be very important. And then lastly, know how to estimate the diameter of the sound beam given the area that you're at. And you will be golden. And that, everybody, is the end of Unit 4.